comités incluyen el Comité de la Hoja de la Ruta Tecnológica Internacional para Semiconductores, la ITRS, el Comité de la Hoja de la Ruta de Integración Heterogénea, la HIR de la IEEE, el Comité de Iniciativa 5G de la IEEE, el Comité de la Hoja de la Ruta del Proyecto de Iluminación Inteligente y el Comité de Becarios de la IEEE. Fue presidente general de la Conferencia de Tecnología y Fabricación de Dispositivos Electrónicos de la IEEE del 2021 y el Simposio de Circuitos Integrados de Radiofrecuencia de la IEEE en el año 2016. Fue director del programa de Fundación Nacional de Ciencias de Estados Unidos y recibió el premio JJ Evers de la IEEE y el premio del Servicio Distinguido de EDS de la IEEE. El Dr. Wang es miembro de la Academia Nacional de Inventores, miembro de la IEEE y por último, miembro de la AAAS. Continuamos con la charla del Dr. Wang y espero realmente les guste y sea muy llenadora para todos ustedes. Thank you very much, Dr. Albert.
Thank you for our introduction. Hola, good morning. Pleasure to be here to give a presentation. And first of all, I want to thank the Costa Rica student chapter for hosting my visit. Okay. And it's my first time to visit Costa Rica. It's a beautiful country over here. And after this presentation, I hope I will have some time to tour around back in San Jose. Okay, my visit is actually sponsored by IEEE Electron Device Society under the Distinguished Lecture Program, the DL program. Okay, so I noticed that this host chapter here actually include both the Electron Device Society and the Circuit and System Society. And I was the DL for the Circuit and System Society, I think 15 years ago, probably. So I covered both of them. And later on, you will also see my discussions actually cover the electron circuit part as well, in addition to the electron device over here. Okay, good. Let's moving forward. So, topic of my presentation is about on-chip ESD protection design. It's more on the reliability side. So, it's for design for reliability of microelectronic product. Okay. Hey, here's the outline. Many of you probably never heard about or never worked with the ESD protection phenomenon or the concept before. So I will give an introduction. And then I will discuss the current status on the ESD protection design. And this is mainly focused on the integrated circuit IC chips. And I will also discuss briefly the future research direction on this topic and end up with a summary. Okay. So, well, I'm a professor as well, so I always start with a quiz, something like that. But some of you saw the solution already. So this is not a real-time quiz. Okay. So the basic question is, what are the two key attributes for almost every piece of microelectronic product? Your smartphone, a laptop, tablet, Wi-Fi router, whatever, the game console control things. What are those two most important attributes? First, performance. We want to use it. We want to get some performance. For example, if you play the game, you want the things very, very fast, right? If you brought the Wi-Fi, you want the data rate very, very high. So those are the performance. Now, on the other hand, you must have a very robust reliability features for your electronic product, because otherwise the product can be damaged and you have to buy another one. Other than you lose the performance, you have to pay a lot of extra money. That's not good, right? Okay, so those are the two fundamental attributes we have to deal with any kind of microelectronic product. Okay, now among all this reliability issue, ESD, electrostatic discharge, the ESD field and the ESD protection is probably the most major problem for integrated circuit chip, the IC chip over here. So I will discuss things in detail later on. Okay. Okay. So part of the reason because the whole microelectronic industry, semiconductor industry, or the IC industry, and the only goal for them to do is to deliver the product and make money, right? And then we can all get a good job, high-paid job over there. So the industry sell IC chip performance for money, right? That's the reason we want to buy them. But if you ask any IC company, semiconductor company, if there's no ESD protection on their IC chip, they cannot sell anything. I will explain the reason later. Okay. Okay. So ESD, electrostatic discharge, and as a technical concept that might be a little new to us, but we actually deal with the things since we are little kid. Okay? You probably remember you go to the museum and you see kind of magic like that. You know, people show you, oh, there's like all the hair stand up over there. And this all caused by the electrostatic charges over there. But when there is a discharge of those electrostatic charge, it may give you some fun phenomena, but it may damage the microelectronic product. Okay, so even in the it's supposed to be a movie. Okay, let me see if the no. It's a video. This is not playing. Okay. Now it's playing. So this was radio from TVs last year sometime showing the lightning hit the new World Trade Center in New York City. And we all heard about World Trade Center, right? This is a new one. Okay. It's kind of amazing things. You see the lightning is actually mega-scale ESD phenomena. And quite often we have to handle with this lightning. It's a mega-scale ESD. So for example, if you go to Africa, do the safari, there will be the lightning over there, right? And you go to Paris, Eiffel Tower, you see the things. You go to Shanghai, on the bound, you see the things over there. Okay? And I'm not quite sure over here, if you have a car, sometimes when you open the car door, you got a little shock over there. In where I live, Southern California, it's very dry. And it's like very frequent things. But here, you know, maybe the humidity level is very high, so it might not be at this everyday issue. Okay, so those kind of things are just annoying. Okay, but sometimes if you don't have good ESD protection, the ESD failure will be very key. So this a few years ago, there's image showing the big jumbo Boeing 777 hit by the lightning in the air. Fortunately, the airplane landed safely. And the reason is because when they designed the aircraft, they have the ESD protection on the plane over there, like at the wing and at the tail over there. So if you pay attention, you actually see a little things on the wing, the little lightning rod over there. And that's based on the ESD discharging concept. Now, another hot topic in recent years is autonomous driving, right? The electric car, the Tesla, or whatever. And Elon Musk has, always tried to tell us, his car is fully self-driving, so that you don't need to do anything. You can watch the video and read the book while the car is moving over there. Wonderful. Okay? But if you pay attention, there is a screen, right? And also on your smartphone or has a screen, computer has a screen over there. That screen is not just the glass. It's not just a piece of glass. It's actually glass contain a lot of electronic component, the transistor, the sensor, or broadly called integrated circuit. Okay, so that things may be damaged by electrostatic charge over there. So that means when you touch the screen, sometimes when you damage the screw, and then all of a sudden, it can be very dangerous. Okay? So it's a big issue. Okay? Now, another thing I think is very important is actually smartphone. So now today, nobody can live without a smartphone, right? And we use it every single second, and you touch it like that, right? And if you open up the smartphone, there's a big PCB board, contain a lot of IC parts over there. All kind of CPU, GPU, or whatever, the wireless chip, things like that, right? And then you have the glass touch screen, as I just mentioned. It's actually the piece of glass with a lot of electronic device over there. Okay, and if you don't have ESD protection, it will be a disaster. Economically, this is for the iPhone 16 Pro. Okay? So if you buy that, it's probably cost you $100 US. Okay? But how much the cost for Apple? Somewhere around $485 US. So what's the difference? The red one is a profit Apple will make, selling each of them almost $700. That's why Apple is so rich, right? Hey, but if there is no ESD protection for all this IC, including the touch phone, then it can be easily damaged, and then you want to send it back for repair or whatever, then Apple will lose a lot of money. So the company care about the ESD failure a lot. It's a big, big issue. Okay, now goes to technical part. So we are all students in the electronic engineering field, right? So I saw the lab over there. I saw students get the lab box over there, the machine box over there, right? So I'm pretty much sure then how to make the key function amplifier is to make a small, very weak signal to a strong signal so that you can drive a loudspeaker to annoy others. Okay. And especially for the wireless communication, the signal from the air is actually very, very weak. Okay. So we learned how to do that. But for a company, when they design, when you hire by a company to design amplifiers, like the ADI or Texas Instrument, or earlier National Semiconductor, where I worked for my first job, you can think it this way. Instead of amplifying the signal, you actually amplify money. Okay, but if you don't have a good reliability, to amplify the money, you are going to lose the money. Okay, so that's a big issue over there. Now, for today's advanced, very, very significant. I'm showing this chart for the inter-circuit technology node over here. So I think you probably heard about the technology, CMOS fabrication, process technology, and digital node, especially in these days it becomes a popular topic. So we're probably talking about 28 nanometer CMOS or 7 nanometer CMOS. And today in the mass production, we're talking about 3 nanometer CMOS. So if you don't have the idea, this dimension means how small we can make a transistor. So if you heard about the AI driven by the NVIDIA H200 chip over there, it has like more than 1 billion transistors in a very small silicon die or wafer like this size over there. Right? So how can you current all 100 billion transistors on the small chip over there? You have to make it small. So the critical dimension right now, we are talking about 3 nanometer in mass production. You get a piece of your hair, you start to cut things in half, continue doing that. You will do a lot of cutting to get 1 nanometer. Okay, so this is a technology node. Now, the y-axis is talking about the typical engineering design costs using this technology for a design. Apparently, this is not a cost when you do the experiment, you construct the PC amplifier in the breadboard for that, right? This is talking about advanced chip design. let's see, by Apple, by NVIDIA over there. Okay. So how much will it cost? Give you an example, like more than 15 years ago, when we first used 28 nanometer CMOS, the typical engineering design cost maybe $35 million for one design, get everything working. Okay. Now, today, if you're looking at the most advanced technology in mass production, we are talking about almost $1.5 billion for one design. That's why Apple and NVIDIA charge you a lot for those designs. Okay, so this is very expensive. Only a few companies can do that. But a lot of other companies doing using less advanced technology, maybe before you this, right? But no matter what, it tells you one thing. It costs a lot of money to design a new product. But if there's no reliability a feature for a chip, your product will fail every single minute. You're not going to make any money. Instead, your design becomes a game like that. Okay, so right now I think only Elon Musk can do that. He got a lot of money to waste, but not everybody else. Okay, so now a little bit more detail. So what is about the ESD? Electrostatic discharge is a phenomenon that produces very fast, very strong current or voltage pulse. You just consider it's a waveform, very fast, and the height is very high, and a lot of energy. Okay, so that will damage IC chips. Okay, and statistically, this kind of ESD damage may cost the industry billions of dollars every year. Okay, it's a big percentage. Okay, so that there is a requirement. We must have ESD protection. And the best way is to have the ESD protection feature for every IC chip. So your smartphone touch screen actually have a lot of ESD protection. So that your touch screens will not damage the screen. And I will explain a little further. Okay. So we have the on-chip ESD. And we have to test it. You design something and you want to verify the design is good. So that in a company, if you work for a company, you can ask for a pay raise, right? For high pay for a reason, right? Okay, so there are many different industrial standards for testing. I'm not going to cover every of them, but I will explain the first one because it's called human body model, HBM. And that relates to what I just mentioned. If your touch screen is damaged, I'm a human body touch, so it's a human body model, right? So let's focus on this thing. It's very interesting. So what is the HBM ESD phenomenon? Okay. So you notice when typically when I do the teaching, I'm working around. And we have a roof over here, and there's a carpet over there. Okay. When I'm working around, especially on the carpet, it will amazingly generate static charge inside. Okay. Even when you are sitting on the chair or in the chair over there, okay, and you're moving around, it will generate static charge. It will accumulate inside your body. Okay, I'm showing over there. Now, inside is IC chip over there, and those static charge inside my body will discharge into the smartphone. It will damage the IC. You don't see that. Okay, because it's very short. Okay, but the current and voltage level is actually very high. I will show you a thing there, right? Okay, so this is danger over here. So that there is a standard for HBM ESD waveform. This is current terminal. It looks like this. But more current is more like this over here. Okay, to understand this phenomenon, people are using equivalent circuit. So there is a capacitor, resistor, inductor. This is an IC. So you can consider this capacitor like your human body. And contain a lot of static charge. Okay, and they just start to discharge. And when they do discharge, your arm has some resistance, right? And you don't know your actually has some kind of inductance over there. So it discharges into the chip. Okay? So this equivalent circuit will be used in the design simulation. Okay. Okay, now more technical detail about the ESD phenomenon. Basically, in terms of the ESD failure, there are two things you have to worry about. One is the ESD pulse is very fast. The current level is very high. And any current run through electron device, you have resistance over there. So it generates power. And then it heat up. But the heat dissipation for IC is very poor. So that the accumulation of the heat, temperature increase very fastly. And then it burns something over there. So this is called thermal damage. It's a very big issue for IC today. Now, the second one is called the voltage breakdown. And this is because you also have a high voltage pulse over there. So it generates electric field. And when the electric field density is very, very high, let's say 10 to 6 volt per meter, the strong electric field density will damage some dielectric of transistor, like CMOS the gate over there, the oxide gate over there. Okay, so those are the two basic ESD failure we call it signature. Okay, so now we understand what's going on and how to do it design. Very simple in concept. We need to find a way to discharge the large ESD current very safely without generating too much heat, without overheating. So that's one principle. The second principle is you want to clamp the IC, the pad, signal pad voltage to a very low level so that it will not damage the CMOS gate there. Okay, so those are the principles. However, principles are just the principles. Whether or not you can do a good design is up to your brain over here. Okay, there are many, many different ways to realize a design. Okay, so for example, you can use like any active device like pin junction diode, BJT bipolar junction transistor, or field effect transistor FET, or the so-called silicon control rectifier device called SCR, or you combine things together, making up a small circuit. So those kind of things will be used as ESD protection circuit for each IC chip. Okay, so this is the basic for design. Okay, so understand things a little further. Okay, so looking up over here, the ESD protection device is placed at I/O pad of an IC. I use this inverter to represent the IC over here. So the ESD protection structure, it looks like a switch. You turn it on and off. Now, during the normal IC operation, when you play the game, you make a smartphone call. This ESD switch will be off. So it looks like it's nothing. It will not affect your smartphone or the game console over there, right? So when you touch the signal of the smartphone, then the ESD pulse coming to the pad. Then you have to turn on the ESD protection device as a switch. Hopefully, it's just a short circuit. No, the whole pulse will be grounded over here instead of getting into the IC internal engines, right? So the protection concept is very simple. Okay. Now, in terms of IV behavior of the ESD switch, it looks like this or this. So this more like a diode. This like we call it snapback. So using the snapback device as ESD protection device as example. So normal IC operation, the switch is off, so you don't have any current. When the ESD pulse comes, it turns on the switch at a certain voltage. There's a threshold. We use voltage, current, and the response time representing. We call it VT1, IT1, T1. And then there's a snapback. The reason we have snapback is because you see here, the voltage is clamped to very low level to avoid voltage breakdown, right? So we use VH, IH to represent this node. And then here, there's a discharging path with a discharging resistance that's called R1. We want this discharging resistance as low as possible. And eventually, there will be a thermal failure because any device can only handle that much energy, right? So the thermal breakdown voltage VT2 and the thermal breakdown voltage IT2 here. So those are called ESD critical parameter an engineer has to design for an ESD protection structure. So the design has something to calculate, to validate. Okay, so this is very important. Okay, now going further, what consider a good design? So again, I use a snapback RV of an ESD protection switch as an example. And then you have some red line. That means this curve has to be lower than the breakdown voltage on your IC chip at any node. Otherwise, it will cause breakdown voltage, right? And then you will also want to make the holding voltage and holding current, or holding voltage higher than the on-chip power supply and holding current higher than the total on-chip current. This is because you want to avoid the latch-up effect of CMOS IC. Okay. Okay, so it's okay. On the top bar, your current handling capability should be higher than the failure current. Otherwise, there's a thermal damage, right? So what does this tells us? This is called ESD design window. Your design or the IV curve must be within the window here. So this is the goal of your design as the circuit design engineer. Okay. So on the other hand, the ESD protection is for the whole chip, whole IC. So illustrate over here. So I'm using inverter represent one part of the IC, and this represent another part of IC. Just think, oh, this is probably just your CPU, GPU, you know, or the wireless transceiver, things like that. And it will have many so-called bonding pads. So the pad 1, pad 2 I'm showing, and then you have supply, let's say VDD and the VSS. Those are all the bonding pads to get the signal in and out of the IC, and also to provide the supply using the battery over there. Okay. And at each pad, you will use quite a few of ESD protection device or structure over there. So the arrow, the red arrow represent the discharging direction of your ESD protection switch over there. Okay. So that when the ESD parts coming over here, one of the switch will be turned on, and there will be short circuit, the ESD parts will be dumped into the ground, not getting inside. This is ESD protection. Okay. Now you can figure the problem, so-called ESD design overhead. Nothing is for free. There's no free lunch in the world. Okay. So first of all, for big chip, there are so many, you could have thousands of bonding pads over there. Each pad has multiple ESD switch. So there, you need to add a lot of ESD structure over there, and it will consume the silicon area, right? The second thing is that so far, most of the ESD protection switch structure, they use a PN junction-based active device. A PN junction means it will have parasitic capacitance, leakage current, noise, and a lot of things like that. Those are things you don't want. Okay, it will affect your IC performance. Okay, you protect your IC, but your CPU starts to slow down. That's not good. I want to keep the CPU a function while protected. Okay, you want simultaneous achieving both function, high performance and the robust ESD protection. Okay, so that makes the ESD design very challenging. Okay. Okay, so there are many emerging challenges for new technology and more advanced chip. I don't want to spend a lot of time on that, but I'm telling you one thing. If you are using more advanced technology, let's say 3 nanometer CMOS technology over there, and you are designing a very complicated chip like the NVIDIA H200 over there, we have 100 billion transistors over there, right? That will make the ESD discharging phenomenon more complex. And then the ESD on-chip ESD protection design will be very, very complicated. You have to handle the design window, you have to minimize the ESD design overhead, all kind of things. So getting more difficult. That's a future research topic. Okay. Now, I'm not really trying to scare you about that, but I want just to let you know, there is a good way to do the ESD protection design. How to design the ESD protection rightfully. Okay. You have to use the scenery or the CAD tool. I'm not sure you have or use the size scenery, right? And that's a circuit level scenery. There are actually many different kind of CAD tool for IC design. For example, you use a so-called technology CAD, TCAD tool to simulate the transistor behavior. Okay, so those kind of CAD tools are required for a good ESD protection. The goal will be design optimization, design prediction. Sometimes there will be co-design. I will talk about that. The whole chip design. So I will also talk about that later. So those are the critical things. Okay. And for the advanced research, you may consider something really novel. For example, as I just mentioned, for so far in probably like 60 years after the IC event, people have been using the p-n junction-based ESD protection switch device, which is inside the silicon wafer for there. That causes some fundamental problems. It's very hard to get rid of that. So you may want to consider something really new. Okay, so that's some advanced research. Okay, so with this introduction to the this comprehensive introduction. So next, I'm going to discuss a few design technique using the real design example. Okay. Now, the first one is about the mixed mode ESD simulation design methodology. And we use a TCAD tool, the technology CAD tool. Now, for us, we use the TCAD tool from Synopsys, the big EDA company. Okay, so the reason we want to mix the mode ESD protection design is because the ESD phenomenon is very complicated. It involves transient behavior, electrothermal coupling behavior. It has something to do with the fabrication process, the materials used, the transistor device used, and the circuit and the physical layout over there. So all those things talk to each other. So we need a mixed mode design approach. Okay, and right now, TCAD is probably the best way to do that. Okay, so I'm showing, okay, here's the design flow. The whole point over here is you have your design target. You will run mixed mode ESD design simulation using the TCAD tool. You will spend a lot of time, in front of your computer until everything works on the screen. And you get all the parameters ready for your ESD protection design, right? And then you send out for fabrication. And we know that IC chip right now in the semiconductor field, the business model is that some companies will only do the IC design, more like do the things on the computer, like Apple, NVIDIA, Qualcomm, all those companies. They don't do the fabrication. And then fabrication will be done by a different type of companies called foundry. And they develop the fabrication technology, like 28 nanometer CMOS or 3 nanometer CMOS or FinFET technology. Okay, right now the most advanced the IC foundry company is the TSMC, the best. Intel has both of them, but they are sort of behind the TSMC in terms of the technology. Okay, so what this tells us that typically, as a designer, you will do the ESD protection design by running the mixed mode simulation, and then you send out for fabrication, and then you get the IC parts. We call it die band. You do the testing. If it works, wonderful. So our target is the first silicon, we call it tape-out fabrication, should be successful. There's good reason for that. You can ask your boss for pre-width. Okay, otherwise, probably pay reduction or you will be fired. Okay, so this is the important thing. And of course, other than simulation, you have to do the verification using different kind of testing methods. So this is the IC die, and you do the normal IC testing, like what is the gain, what is the frequency, things like that, what is the data rate, and then you do the ESD testing using different testers over here. Okay. Okay, so let me show you one practical design example. So in this example, we use a mixed mode TCAD simulation flow. So the core IC means it's core IC. Let's see, it's a GPU or CPU with 1 billion transistor over there. And each bonding pad has an ESD protection structure. It's a blue box over here. And then this CRL circuit is an equivalent circuit of human HBM model ESD equivalent circuit. We discussed it before, right? Okay. So what do? You run the simulation. You use the circuit to produce the ESD powers, which will be used to stress the whole chip. And it will then use the TCAD to simulate the ESD behavior over there. And you will get a lot of ESD parameters to evaluate. Okay, so this is general idea. Now, specifically for this example, I'm using two ESD protection switch structure. One is a relatively old one, is called ground the gate M.Sc. It's a FET structure, so called GG-M.Sc. The other one is more advanced, is called gate coupled M.Sc, the GC-M.Sc. Okay, they look like this. The ground gate, you see this FET M.Sc transistor over here. The gate is ground over here, so we call it ground gate GC. And the GC-M.Sc, you see the gate has RC coupling here, so we call it GC-M.Sc. Now, the reason I use the example is because for probably like 30 years before, people use the GG-M.Sc for ESD protection. But this has a fundamental problem. The trigger voltage, if you recall, the VT1 is kind of too high. And that's too high, it's not good for low voltage CMOS design. Why do you worry about the low voltage design? Well, it's important to us because our smartphone, we have to charge it every day, right? Okay. So right now, a good one, you probably only need to charge it like every other day, depending on how often you watch the TikTok, right? But in the old days, you probably have to charge it every hour. It's actually there's a business they sell the battery bank, right? It's all about this low voltage design. If you have a low voltage design, CMOS, that means your IC will consume very, very low level of energy. For the same AAA battery, it probably will last for 1 day or maybe for 1 week. But otherwise, you will have to charge your smartphone, every second, right? So this is important. But unfortunately, the ESD trigger voltage VT1 for this GG-M.Sc is kind of too high. It's not good for low voltage design. So people invent the GC-M.Sc. You can imagine the trigger voltage VT1 will be much lower than this one. Okay, so this is the basic concept. Let's look at the simulation. Simulation tells you everything about the thing. Okay, so the upper part here is to simulate the GG-M.Sc ESD protection switch. The right-hand side over here is a human body model ESD waveform. You see, you recall I showed you before rising time, falling time, right? There is a rising time over here, and there is a duration. The total area underneath the waveform is the electrical energy the ESD protection device has to handle. Okay, and then the most important thing is this, guys. This is IV. And if you let's pay attention to the blue part only, the red part is more complicated issue with the CAD tool. Okay, so you see the ESD switch GG-M.Sc stay off, and then it turned on. There's VT1, and then snap back, and it's holding, and then start to discharge. This is what we showed before, the ESD design window, snap back curve, right? Okay, now with the simulation, you can see how much is my trigger voltage VT1. So this one is like somewhere around 15 volts. This is like too high, crazily high. Okay, because we use old technology to demonstrate it. Okay. And actually we did it a very long time before. And of course, there are a lot of other parameters. For example, what is the response time? So you put this waveform in the time domain, and you find the trigger threshold here, corresponding here. You can find out how much is the T1 response time. Right now, it looks like 0.1 nanosecond over there. Okay, it's fast enough, right? Okay, but this is too high. We want to reduce that. So we use a GCMOS. Okay, with the GCMOS, you see the IV curve of the ESD switch is off, and then turn on. So you find the VP1 over here. And then there's a step back. Step back, the holding voltage is almost the same as that one. And then start to discharge. Okay? Now the key thing is this one. That one, VT1 is 50 volt. This one, VT1 reduced to maybe like, I don't know, 7.5 or 8 volt. So good. It's good for low voltage design, right? Now, how do you do that? As a designer, you have to choose different resistor, capacitor, change the value, run the simulation again and again, and get the exact waveform. And if you want to consider the different other parameter like the gate voltage, you can see that one. And again, in the time domain, you can see this one over here. And this is turn on threshold, and you find the T1. T1 almost the same, but it actually changed. It actually doubled from like 0.1 nanosecond to 0.2 nanosecond. It's slower, but it's still good enough. Okay, so this example is verified experimentally. Basically shows you how do you run the TCAD tool to design the ESD protection structure to get a better ESD protection design from GMOs to GCM. Okay. So this is one interesting example. Now I'm showing another example using the 3D TCAD simulation.
See here, you see the schematic for the DEC that you showed like to
The model.
the schematic. That's one.
What?
Yeah. Because I cannot read the. Is there a 10K resistor under one?
Oh, okay. So here, this specific example, we set the initial condition for the capacitor to HBM 2 kV 2000 volt over there. And this is just one example. So what about this 2000 volt? Basically, your body accumulates a lot of static charge, and then you touch the IC. There's a waveform generated, right? So I mentioned the waveform current and voltage waveform very high. How high is that? The voltage can easily go beyond 1000 volt. Right now, you are probably talking about 30,000 volt. That's a very high voltage, right? Or the war electricity supply, I think in Costa Rica is like 110 volt. Or 220? Oh, 120. Okay, 120. It's only 120 volt. Now this is at least this example is like 2000 volt. Okay. So even for the 120 volt, you don't want to touch that in your feet. It will kill you, right? Okay. But then the question is, we're talking about the ESC phenomenon in the smartphone. So I have ESC power up to 2000 volt. How could I stay alive? Because the period duration of the pulse is very short. We are talking about like millisecond or whatever. And it's not like constant touch over there. The total energy is small, but the voltage is very high. So that's one thing. Now the other thing is the current. The current level is also very high. You can easily go to like a few tenths of amp. Now you probably don't have much idea about this amp in current. In the IC design, there's a current over there on your computer, the GPU chip over there, right? How much the current? The voltage that we are talking about micro amp over there. Okay, so it's 10 to minus 6 amp, very, very low. Now your ESC powers generate like 10 amp. Imagine it will damage your IC immediately. Okay, so those are numbers I used to characterize how robust is your ESC protection. That good?
Yeah.
Great. So the 3D part, why do we need to do the 3D? Because consider an IC chip. It's a 3-dimensional silicon chip over there, okay? And you have to do the layout. There is X dimension, there's Y dimension, there's Z dimension over there. And there is always the edge and the corner of your IC chip. And because ESD phenomena introduce a lot of heat, and because ESD pulse is very fast, and the heat cannot be dissipated, so it will generate a local hotspot. Okay, the hotspot will be inside. So locally, it will burn up the chip, right? Okay, so this is the problem over there. A hotspot apparently is a 3D entity over there, right? So you could imagine if there is an edge or there's a corner over there, it will cause the current clouding. And the local heating, the heat will also cloud. So on one spot, it could be too hot, the other area could be okay, right? So it's just like a volcano, right? So the center part of the volcano is very high temperature, but here is okay. So we need to do the 3D simulation because IC design, the layout is kind of 3D. Okay, so TCAD tool can do that as well. So I'm using one example. So this example, the ESD switch is actually using a PN junction diode. It's a P plus N-wire diode over here. And the switch has two terminals. One is anode, we call it A. The other one is a cathode, we call it K. And just think about this PN junction diode, two terminal over there, right? And this connect to the IC bonding pad over there. Okay, so this is a two-dimensional. And look at the three-dimensional thing. Okay, so in this example, we designed this one over here. This is a PN junction here, but on top, you had to use the metal plug to get the current in and out. So this little bar represents so-called contact metal. So upper part, let's consider is anode. So I have 6 metal bars there to conduct current. Lower part is the cathode, same amount, 6, to drain the current. Okay? Okay, so you have large ESD parts dumped into A anode and then discharged into ground through the cathode, right? Okay, so apparently I want this ESD large current, let's see 2 amp over there, can be flowed through this ESD protection structure very uniformly. So there will be no hotspot. That means if we die, let's die together. Okay, so let's keep on. But that's not a situation because there's dimension. You could imagine there could be some kind of crowding here and here, or maybe here, or maybe here. We don't know. Let's run the 3D simulation. So as example, this split 1 and then split A, split B, because of simulation, I can ask all the current to run through this metal contact only, not here. If you pay a little attention, there's a little pink color over there in the simulation, even though physically you have this metal plug over there, the contact plug, but you can block the current here. You only allow the current to go here. So all the current in this design will goes to this edge, could be over here. Okay. Now, split C, I have more smaller contact metal. The total area are the same, but it's smaller. So you can imagine, oh, this is probably better to inform the current, the discharging uniformity, right? Okay, so the split D, because we have this structure like this, the internal part, center part, maybe over here a little more because there's a coupling effect. Here, there's a window over there. So there's a heat dissipate over here. So center part may be hot. So consider that we will revise the IC design in terms of metal contact. Center part, the contact is smaller. It will have lower current. Edge part, the contact is bigger. It have more current. So the center part heat will be lower. I want to get things more uniform, right? Okay, so let's see the simulation by the 3D. Okay. So if you consider split 1 versus split 2, so the color map shows you the temperature. Apparently the red like the volcanoes, it's too hot over there, right? Okay, so this is just image. What about the number? If you look at the maximum temperature in the time domain. For split 1 is red one. Yeah, red one is okay. So the temperature somewhere around maybe 400 K. Okay, higher than the room temperature. So it's more like summertime temperature. But this one, a lot of overheating. Then you see the temperature overshoot to beyond 1700 K. And then will burn up the IC. So that's not good, right? So this shows in 3D, you don't want this kind of design. Okay. And the ESD discharging curve also changed. Okay. And then let's compare to split A with split. Oh, sorry. This should be C. This should be C. Okay. So more smaller metal contact, but total area is the same. Now you compare. Okay. So the red one is again that one. So temperature is this much, like 440 K over here. But this one, you see the blue one, the temperature reduced over here. And maybe reduced by like 30 volts or 40 volts, 40 K temperature degree over here. That's good, right? What about compared to the split C? So the center part metal contact smaller, less current, and the edge contact bigger, more current, and compare C to thing. So for the original one here, this is temperature 440 K degree. And this one is lower, but still higher than this one. So it probably only like improved by like 10 degrees easily, right? So this 3D simulation tells you exactly how to improve your design. Okay, so hopefully it's interesting. Okay, now apparently I have time limit. I'm going to pick up another interesting example. I have to skip over quite many slides. Okay, so next example, I want to show you how important ESD protection is for RF circuit. So RF, radio frequency, why do you care about that? Because you use a smartphone. Smartphone use wireless communication technology. And what deliver the wireless communication? RFIC, not CPU. Okay, CPU get the image, but then you have to send it out to your body. Then you can, communicate, right? Okay, so that's important RFIC. But RFIC is more sensitive to any kind of parasitic effect induced inherently by ESD protection. We talked about the design overhead, right? Parasitic capacity, the leakage, noise, all kind of things, and also the size. Okay, both factors are important because the capacitance, noise, leakage current, it will affect your RFIC performance. But that will affect your Wi-Fi downloading speed. We are talking about 100 megabit per second or 1 gigabit per second. So that's affected by those parameters. The other thing is the size. Okay? If the ESD structure size is too big, then the die is too big. Not only your smartphone will get this big, but also it will be more expensive. Okay? So those are the effects we have to do that. But the ESD protection structure, it exists physically. So as long as it exists over there, it will always has a bad effect, parasitic effect, right? So that you have to consider the balance between the ESD protection and your RFIC performance. So you need to do the co-design. Okay, so the co-design is a very important concept today for RFIC design with ESD protection. So I'm going to use this example to show you how big is the problem and how good could be co-design. Okay, let's first see the problem. The problem uses the low noise amplifier as an RFIC. So low noise amplifier is called LNA. Why do we call it low noise? Okay, so you think about your smartphone. You receive a signal, you talk with your mom or whatever it is. The voice comes from the power and then to your phone. And it's very, very weak. And then you have to use an amplifier to boost up the signal, right? Okay, but your mom's voice comes flying through the air. When it reaches your smartphone, there's a lot of noise. Okay, So you have to use a noise sensitive amplifier. It's called low noise amplifier. Okay, so there's a special circuit for RFIC. So this is a circuit schematic for low noise amplifier. And it's a little bit interesting, but we don't want to spend much time. The key thing is you need to have ESD protection at the input end over here. Okay, so finished up design, and this is a dye photo of the fabricated low noise amplifier. And there's a ESD protection switch that's over here. This is input, this is output to the internal, the digital processing unit over here. Okay, and this was fabricated. What technology? I believe in the relatively old technology, and the center frequency is 5 gigahertz. So I don't know how the technology no, but anyway, the parameter for low noise amplifier characterization. Number one is the gain, which in the S scatter parameter for RF that's called S21 parameter. And the input signal, there's a reflection signal loss. Is characterized by the S11 parameter. And then there's a noise characterized by the noise figure NF. Okay, so those are very important parameters for RF circuit low noise amplifier design. Okay, so let's compare with and without ESD protection. This same LNA circuit die, you have the ESD protection, and you measure the parameter. And after that, you notice there's a long neck wire. So when we did the design, we did it purposely because we want to measure this LNA circuit with the ESD protection and to see what the impact of the ESD protection on the LNA circuit. Okay? Then after that, for fair comparison, we will use a laser to cut off this metal so that this ESD structure will be physically removed from the same RNA circuit. And then you measure this RNA circuit only without the ESD protection. And then you compare these two cases. Then you will see what will be the impact, negative impact of ESD protection on RNA, right? Okay, so let's look at the measurement result. RNA circuit only without the ESD protection. This is again 18 dB input signal reflection minus 8 dB and the noise 2.99 dB. And then you have the ESD protection structure for 2 kV ESD protection. Okay. You see the gain reduced from 18 dB to 15 dB, dropped by 3 dB. But signal loss and input increased by 1 dB. And the noise also increased by like 0.2 dB. So negative impact, right? Wait, so you may say, oh, this is like noise is just only very small, right? But in the future, if you work as an RFIC design engineer in a company over here, and if you code improve the noise figure by 0.1 dB, you get P rates. Okay? It's very, very difficult to design to get 0. something dB. Okay, dB is it's just a ratio in the decibel, right? Okay, so 20 log gain is a dB. Okay, okay, so it's important. Now, even for the curve, this is noise and this is frequency. 5 gigahertz center over there. You see from 4.5 gigahertz to 7 gigahertz. You measure. Okay, so the pink one is the noise figure for the RNA without the ESD protection. And the blue one is the noise figure when you add ESD protection. To subtract these things, you get a pure contribution of noise from your ESD protection. It's fluctuating, but it's quite significant. Hold something, it's big. Okay, that means when you make phone call, your mom's voice will be distorted. You cannot hear clearly. So this is very important. Okay, so apparently you have to optimize your ESD protection design for by minimizing all the parasitic effect. But that's a big story. We don't want to spend much time. And okay, I'm moving to the next topic, which is co-design, just to show you, how important is that. Circuit design simulation. Okay, so this is an approach. the schematic of your co-design. So this is your RF circuit. Let's see it's RNA circuit. This is input, this is output. In the RF circuit design, because it's high frequency, so think about your Wi-Fi, 2.4 gigahertz, 5 gigahertz. So this kind of trick, the store tries to sell you. Oh, I have a 5 gigahertz. What are that? It's just the center frequency. Hopefully translating into higher bit rate, right? Okay, so there's a technical issue there. But because of high frequency, then the input to the internal circuit or output to the internal circuit, there is an impedance matching issue. It's called a Z matching, impedance matching. Okay, it's very important. Number one, important thing is in RF design. Okay, so basically, you design the RF circuit wonderful, and you also design the impedance matching wonderful. Okay, but you need the ESD protection. So you have to design the ESD protection structure. Maybe GGMOs, maybe GCMOs, maybe a PI, or maybe SCR structure, okay? And after that, you fabricate that, you do the measurement. You try to extract all the parasitic parameters of your ESD structure, like capacitance, like the leakage, like noise figure over here, okay? So after that, you have to redo your RF circuit simulation by including all those extracted parasitic parameters of your ESD protection structure. Okay? Now, the reality is everything will change. Your RFIC performance will degrade. It's because impedance matching is distorted. And they have to do the design optimization. Okay? So you run the simulation, you keep changing your design, and here you have both ESD protection and your RF circuit performance good enough. Nothing's perfect, but still enough. So that's called co-design. Okay. So now let's show the co-design example over here. Okay, here's a co-design example. A different RNA circuit. Okay, so you see the circuit schematic is a little different. This is a cascade structure. And you see all those inductor, capacitor things, those are the impedance matching at the input end and output end over here. And this is a diphoto of the fabricated RNA circuit. And the input end has a ESD protection. And this was designed in the 180 nanometer RF CMOS. Okay, ESD protection is 5,000 volts, and those are the circuit performance. Like the gain is a 14 dB, noise figure is a 3.12 dB, things like this. Okay, then let's look at co-design. Okay, so basically we have two group of curve. The upper one is from simulation. The lower one is from a measurement. Okay. And we focus on three key parameters. One is the gain, S21. The other one is input reflection or loss, signal loss, S11. And then the noise figure, NF over here. And across several gigahertz, center frequency, 5 gigahertz, and then it's like from 4 to 7 gigahertz, very wide band over there. Okay. And to see the ESD, the negative ESD impact on your RFIC, we try to use a different ESD structure. Okay, so what we use here, including the GGMOs, very traditional one, but this is not very good because it introduced a lot of parasitic parameters. Okay, and then we use a pin junction diode. This is much better, but it still have a negative impact. And then you have a co-design split. Use the use the diode over here, and then everything will be compared to with the RNA without the ESD protection, the original one, to see what the difference is. Okay, so this is a split. Okay, if you look at the simulation versus the test, it looks like they are very similar, right? Okay, so let's focus on the measurement again. Okay, so first let's see the gain. Okay, so the gain, original one, the RNA without the ESD protection is a black curve over here. So let's see the peak gain somewhere around the almost 15 dB, right? And then, excuse me, you use the traditional GGMOS ESD protection, which is this guy over here. What do you see? The gain jump, crazy, right? Okay, not good. Okay, so you don't use the GGMOs for RFIC ESD protection. And then we use a dial, which is a cross. So it's not very clear, but you can see something over here, right? So there's a jump. It's much better, but there's still a jump over here, right? And then, and then you have the co-design. We do the impedance match on whatever. So you get the pink circle over here. So over here, especially this end, you see it increased back from here to here. So it's better, right? Co-design is better, but it's not very clear. Wait, let's look at a second parameter, the S11 parameter at the input end. So the area A without the ESD protection, you have this one. So the value here means the signal loss at the input is very, very low. So you want that over here, okay? But if you use the GGMOS ESD protection, what do you see? At center frequency, it's a huge loss over here, right? The loss is like almost a 20 dB loss. That's not good, okay? If you use a diode ESD protection switch over here, you get this one. Much better than this GGMOS, right? But center frequency is still some signal loss, a few dB, okay? And then you do your co-design. You see, perfectly, everything matched for the RNA circuit without the ESD protection. Perfect, right? That's why you want to do the co-design. Okay, what about the noise? So for the noise, without the ESD protection, you get a black one over here. Noise level kind of low, pretty low actually. And if you use GGMOS ESD protection, noise increase a lot. And you use diode ESD protection, you get this one, this cross mark over here, it increases slightly. And after co-design, you get a circle one, it reduced the noise, but still higher than the original RNA, right? Okay, so what does this mean? This example, I hope to give you an idea, showing that RF ESD co-design is very useful, very important. Number one. Number two, for different circuit parameters, the behavior may be different, or the optimization result may be different. Okay, so that tells you that in a practical circuit design, you do not expect everything will be perfect. That's impossible. Okay, a practical IC design, you always try to balance the different design parameters. The ESD protection is required, but it introduces parasitic effect that affect your RFIC design. And then you have to optimize your design. And here you have good ESD protection. In the meantime, the RFIC performance is still acceptable. Design balance, okay? And that can all be done by running the simulation using the co-design approach. And hopefully you can validate that in the magic. Okay, so I still have a lot of examples. I don't want to talk too much, and we don't have enough time. So I'm quickly moving to the future direction. Okay, so in the future, what will be the technology? One is the ESD design and the process technology should be co-developed. Earlier, we're talking about ESD RF circuit co-design. But for fabrication for TSMC, the foundry companies, you get CMOS 3 nanometer, or today they are working on 2 nanometer, right? So you have to do the co-development, okay? Because in the old days, company always start working on the CMOS for the transistor performance first. And then they started looking into the ESD failure issue. Okay, and then they have to manipulate the technology. That means it takes longer time, and they use more money to qualify an IC process. In the old days, it's okay, but for today, it's too expensive to do it that way. So we need technology co-development. Okay, This is one of the direction. Second one, we need a holistic ESD protection. Other reason is because the chip is getting more and more complicated. In addition, you have analog part, you have RF part, and you have huge circuit with 1 billion transistors over there. You have different power supply. So all those physical and functional circuit domain, they have different ESD requirement, and the impact of ESD parasitic effect on the circuit will be different. So you have to consider as a whole, it's called holistic method. And that becomes more important for today's chip using the heterogeneous integration. I think we'll touch it the next. Oh, yeah, here it shows. Now, today's technology, we do more and more for heterogeneous integration. That means you use different IC die for different functions. So traditionally, you have analog, digital, RF. You have high voltage circuit. Let's say you use gallium nitride for the electrical car over there. Okay, and then what? You need sensor for your smartphone touch screen. There are a lot of capacitive sensor over there, right? You need a navigation. And we use accelerometer, the kind of device over there. They are not in silicon. So all these different functions will be delivered using different materials, different circuit structure. And they want to put things all together, physically together. Okay, so each functional circuit is called a chiplet. And then the whole circuit will be a chiplet-based circuit. It will be heterogeneous integrated. So now, as I just mentioned, you also have advanced packaging. For example, over here, traditionally, you probably only have one silicon wafer. Okay, now you have a lot of different things. This is CPU, GPU for AI, power management IC, analog mixed signal, RF, the sensor, optical, and high bandwidth memory over here. So they're all together and putting on the carriers called interposer over here. So that makes the ESD phenomenon more complicated and the ESD protection design more complicated. You have to consider the whole thing together. It's called holistic. Okay. Okay. Now, another important thing is that the new CAD algorithm for ESD protection design. So I discard using TCAD. I discard RF simulation. Okay. Those are good enough, but they are not wonderful yet. Because to do the ESD physical design verification, you need a new CAD algorithm. There's no commercial tool yet. Okay, so we have work on that. The flow can be very complicated. And then we have the new phenomenon. Okay, what the new phenomenon will be? As I mentioned earlier, so far, for maybe like 30, 40 years, people always use they always introduce quite significant parasitic effect, capacitive leakage noise, right? But as long as you use those things, you can optimize the ESD design, but there's no way you can make the parasitic effect zero. Okay? You have to think something really, really novel. So I'm showing one example. This actually using the graphene-based mechanical switch as an example for ESD switching. So this is your internal circuit. Here, you see the cross section here showing there is a silicon cavity and then graphene membrane over here. And then you have two terminals. One is the graphene connect to the ground, and the other one is the silicon connect to the I/O pad over here. Okay. Now, because of the cavity over here, what do you see? There will be almost no capacity ideally, theoretically, right? There should be no current. And the noise will also close to zero or ideal. Okay. When the ESD pulse comes to the I/O pad, then the graphene ribbon will be pulled down by the strong electrostatic field. So it starts to bend until it touches the silicon. If you touch, it short circuit, right? So it's just like a mechanical switch, off, on, but there is a cavity over there. There's no pin junction. So all those parasitic effects associated with pin junction in silicon can be removed, right? But apparently it's very difficult. But we demonstrate things, at least in some prototype. So this structure, you see here, this is the diphoto, this is the graphene ribbon, and then the darker part is actual cavity over here. And then this is IV curve for the ESD switch. You see forward turn on like a die, reverse turn like a die. It's not a pin junction die, but it behaves like a die. It's a switch. Okay, so this is one of the direction. Okay, so almost there. Let's look at the last one I want to sort of promote. So using AI technology, machine learning, large language model, or whatever. The general idea is, as an individual circuit designer, you could be really smart, but your knowledge is just limited to your brain, right? Wait, ESD phenomenon is very complicated. There are a lot of different design, different knowledge over there. If we can group all the talents around the world together and putting all the knowledge in the simulation tool and library, it's like use AI for ESD design. So I call it open ESD forum. So the whole idea is not rely on one brain, but try to get everything. So it's more like the large language model, but it's a ESD specific, or we call scientific AI. Okay, it's just not just for fun. It's knowledge based way. Okay. Okay, so to conclude, I just discussed is that it is a very important ESD reliability problem associated with semiconductor or microelectronics. Okay. And so that we need on-chip ESD protection. And I discussed the state of art for ESD protection design. Okay. And I give you a little future perspective. Okay, so hopefully this give you a good idea about the ESD protection design. Some reference if you want to refer to, or you can read my. Okay, so I'm good with this presentation, and I'm open for any kind of questions.
Perspective forward, the thinner for the finish.
Yeah.
No.
Earlier one? Yeah. Yeah.
Talked about the pin black like a switch, but the graphene, it isn't the same material in those parts of the sides. Yes. How would last? How much will this film last? Because it is mechanical movement.
Mhm.
How can you calculate the long life?
So how could this film be locked to the structure, right?
Yes.
So it's pinned down over there, right?
Yes.
So it's more like this is a film. So it's like over here. I hold it, and I only allow the arm bend, right? So this part, only this part of my body will be. It's like this. So here specifically, this graphene beam is actually contact on the edge of in this case it's a silicon nitride over here. There is physically or chemistry, there is a healing force over here. Okay, they were sticking. But you can imagine if this is a mechanical movement constantly, there could be a cooling effect. Okay, so eventually, I guess your concern could be if you put it too much, it will just slip over, right? Fall down. And that's actually one of the problems. You have to solve it in your physical design. Okay, we actually did some design. We tried to use kind of like a nail to hold the, it's like if this one pad, use 3 nails over here, but this is not a nail. It's just some physical structure over there. Okay, so you have to hold it, otherwise the membrane will collapse on the bottom. Then, yeah, it will not bounce back. Okay, so the reason this can bounce back is because graphene is very special materials. Graphene has, first, it's very light. Okay, second, it has a very, very high Young's modulus. That means it's very rigid, and you can pull it with very strong electric field force over there. Okay, but as long as the force disappears, like this, it will bounce back. It's very strong. Okay, so this is the trick in the design.
It's thinking because this bouncing, this connection. Well,
I do believe that the questions like referring to the mechanical wear of the graphene. So if I understand you correctly, that it will eventually wear like when you have a switch that eventually will.
It's like a screw.
Yeah. So is there any mechanical wear in the graphene? So it will break eventually because of the.
That's possible. Okay. So again, here what I said here is a graphene membrane or the ribbon or whatever. But you imagine it's just a spring. You hold 2 ends of the spring. You just pull the spring and it will bounce back, right? Okay. Apparently it could be broken, right? So this is another reliability problem for this mechanical switch, but it's different from the ESD reliability problem that we try to address. Okay, so there is a mechanical issue. Now, this is the reason we use graphene, because graphene probably is today the most, the strongest mechanical structure you can achieve using these materials. The Young's modulus is very, very high. And this is also good because it's very rigid. That means the frequency can be very high. So the response time could be very high. Because if you use, let's see, if you use just a piece of string over there, you can pull it down, but then it will bounce back very, very slowly. Okay, it's too soft. So mechanical reliability or mechanical failure is actually all the rupture things. It's actually a concern of using this kind of the structure, and that's the reason it's a research. Okay, nobody really use this in the real IC product yet. Complicated.
We don't tell our boss about it.
Okay,
We solved the ESD problem.
Yeah.
There's another problem.
Yeah, that's right. The problem is one after the other. Okay. Okay. Any other question?
Dr. Wang, at the beginning you said that when you talk about the principles of ESD, you said that we want like to, but let's say to send that impulse, that ESD impulse, like to ground or at least say away from the ship, or they say in that moment, well, the functionality gets like interrupted, or is it like something us as engineers have to take into account in other part of the circuit?
Okay. Probably see it over here. I guess your question is the ESC structure is switch, and the ESC protection works in a mechanism that when ESC powers come into the pad, switch is on, the ESC powers will be discharged into the ground through the short circuit. Is that right?
Yeah.
And you worried what about the chip function here, right?
Yeah, I mean, like let's say it's a signal. And in that moment when we remove all the ESD protection,
okay, I think I got it. So there are two things over here. One is your CPU is working. Okay, you are playing the game. Okay, now while you are playing the game, your body come here to downlock the ESC, the static channel, generate ESC pulse, right?
Yeah.
Then at this moment, your number one priority is protect your smartphone or the game player packaging, making sure it's safe. It will survive. It will not be damaged. So you don't worry about the game at this moment. Okay, when the pulse is over, the switch is off. Then you go back to your game. Wait, that sounds like not a good idea because you have it turn on and off, right? This is not a mechanical work. You get the door on and off. It's very slow. Electrical work, we're talking about picosecond response. You don't even fear that. Okay? Your body touched it and create danger, and your ESD protection turns on. At this moment, there's no game, but the game will recover in 100 picoseconds. You don't even notice that. Okay? So, yeah, two separate functions. But you have to make your ESD protection very, very fast. And that's the reason later I show the graphene-based mechanical switch. That sounds good, but if you use a switch like we have the light switch over there, the old one is turned on and off, that would be too slow. Okay? So it doesn't work. Okay? So you always consider the balance. You cannot say, I have a wonderful mechanical switch, okay? With zero parasitic capacitance noise and leakage, just use it. But it's too slow. Other than it's too big, right? It's actually a good question. It's two different things, but you have to balance both needs. There's overall consideration for the system.
So in fact, there is an interruption, but it's really, really fast.
It's really short. Okay, so at the time when ESD comes over here, your number one concern is to survive. It's more like somebody want to kill you. At this moment, you fight back. That's the important thing. Okay, everything else is not important. Okay, but you need to be able to recover. Okay, that good?
Yeah. So I have two questions. One is really short. In the schematic, it's just connected as a diode. The MOSFET is just connected as a diode, isn't it? So I believe in the next. No, later. The same that I asked earlier. The one with the CG, that one. The last one. Yeah, so the GG, the before this one. One before. This one, it's that MOSFET is just connected as a diode. That one.
Here, okay. So this uses the MOSFET as a switch. Here, this gate is connect here to the source. The source typically is ground. That's why we call it grounded gate.
Yeah.
This one, you see at the gate, it uses a capacitor and the resistor as a coupling effect. So it's called gate coupler. This gate is not ground. The reason we need that is because we want, when the ESD pulse coming over here, it will raise up the gate voltage. The gate voltage increase, then the substrate current will increase, and then it will turn on the FET structure quickly. And actually, going further from the device physical viewpoint, it is actually a parasitic BJT transistor inside FET is turned on. Okay, but there's too much device physics over there. Wait, so as a designer, you have to choose different value for the specific structure and the layout to make sure this is the right gate bias voltage and translate into the right trigger voltage. You can see here, I actually shows the gate voltage here. You see, you can change the things, the gate voltage will be different. And the different gate voltage will change the trigger voltage. And all this are affected by those RC coupling network. So a lot of detail, the concept is very simple. But a real good design, you have to run our simulation. Okay? Good. Anything else?
The other one is, what happens if the voltage doesn't enter our ESD discharge system first? So what happens if it's in another part of the circuit? Because I believe it's
okay. So that is your question is more related to the turn-on speed of the ESD protection structure and the internal circuit, right? So when the pulse over here, what if the internal circuit is affected first, even though you have a ESD structure, right? So that depends upon how fast your ESD switch can be switched on. And that is characterized by the triggering time. You see, you probably have the same value over here. Let's see over here. If you push this node to the right, it will be slower. So at this moment, the response time of the ESD switch is somewhere around like 0.1 nanosecond. But after this, you can see here, this is actually slightly slower, but it's not quite visible. What if you push it over here? It becomes like 1 second, and that's too slow. Okay, so you have to design the things for the transient behavior. Okay.
Thank you.
I have a question about the graphs of the response time. We are looking like exactly the moment of the voltage, the peak voltage. What I'm guessing, I'm trying to understand what is the information right to that peak voltage peak in the response.
The water peak over here.
Yeah, like on the right, is that information important for the design?
It is important because, look, in this example, I actually use HBM ESD model, meaning the ESD power is coming from my body. Okay, this is just the one part. Okay, now the waveform has a rising time. Okay, so here it's the ESD heating not a concern, but here is a concern, right? So compared to the switch, you want the switch to turn on somewhere here. If the switch turn on here, then you've got a lot of overheat already. Okay, so it's there. Wait, for a human body, you have this waveform, but there are other types. We call it machine model, called the charge device model. Okay? Those models, in terms of the ESD pulse waveform, the rising time is actually very different. Human body model, this rising time is typically like 2 to 10 nanoseconds. So your response time of 0.1 nanosecond is good because ESD rising slowly in 10 nanoseconds, but your switch turned on in 0.1 nanosecond, right? You are faster. But if you consider the CDM model, the most current phenomenon, it's about rising time of the waveform is about 100 picosecond. Rising time is 100 picosecond, but your switch response in 0.1 or close to 100 picosecond. There's competition, right? But if you go over here, let's see, it's 0.2 nanosecond. Then your ESD protection switch will not work, right? So timing is very important in terms of dealing with different ESD phenomena. Okay? Different danger, you have different weapon. Okay. Okay. Any other question? Okay. Thank you so much for your attention. Okay. Good.
Gracias a todos por realmente asistir a esta charla, realmente nos llena